2,000 meters beneath your feet, deeper than the deepest mine, hotter than boiling water, under pressures that would crush a submarine. There is a pool of oil the size of a city. No one has ever seen it. No one has ever touched it. No one has drilled a single hole anywhere near it. But a team of geoscientists sitting in a control room 1,000 kilometers away has just made $100 million bet that it is there. A bet based on sound waves, gravity readings, magnetic fields, and a geological model built from rocks that haven't seen sunlight in 200 million years. This is how oil companies find crude, without digging a single hole. This is the hunt. I am Chris, the maritime economist. Here is a problem that most people never stop to think about. Oil reservoirs are not lakes. They are not caves. They are not empty spaces underground waiting to be discovered. An oil reservoir is a solid rock, typically sandstone or limestone, saturated with hydrocarbons. The oil occupies the microscopic pore spaces between the rock grains, and this rock is buried 2 to 5 kilometers beneath the surface, under pressures of hundreds of bars and temperatures that can exceed 120 degrees Celsius. You cannot see it, you cannot reach it, you cannot sample it directly without drilling a hole that costs anywhere from $10 million to over $100 million, depending on whether you are on land or in deep water. And here is the brutal reality of exploration. Historically, only about 1 in every 5 to 10 exploration wells actually finds commercially viable oil. In frontier basins, regions where no oil has been discovered before, the success rate can drop below 1 in 10. Every dry hole is a financial catastrophe. A single deep-water exploration well in the Gulf of Mexico or offshore West Africa can cost $40 to $80 million. If it comes up dry, nothing. Zero. The money is gone. There is no partial refund. There is no salvage value. The hole is plugged with cement and abandoned. So before anyone commits to drilling, the question must be answered with as much certainty as physics and geology can provide. Is there actually oil down there? And answering that question, or reducing the uncertainty from a coin toss to a calculated risk, is the job of petroleum exploration geoscientists. It is one of the most technically demanding, financially consequential, and intellectually elegant disciplines in all of science. The hunt begins not with a drill, not with a seismic truck, but with a map. The first and most important filter in petroleum exploration is the sedimentary basin. Remember from episode 1, oil forms only in sedimentary rocks that were deposited in ancient oceans and lakes, rich in organic material and buried deep enough to enter the oil window. That means the very first question an exploration team asks is brutally simple. Is there a sedimentary basin here at all? If the answer is no, if the rocks are igneous, like granite, or metamorphic, like schist, the search ends immediately. You will never find oil in granite. The geology is fundamentally wrong. Once a sedimentary basin is identified, the exploration team begins asking a series of specific structured questions, questions that form the backbone of what petroleum geologists call a petroleum system analysis. Was there a source rock, an organic rich shale deposited in a low-oxygen marine environment that entered the oil window? Was there a migration pathway, a network of permeable rock layers and faults that could carry the oil from the source to a reservoir? Was there a reservoir rock, a porous and permeable sandstone or limestone with enough space to store commercial quantities of oil? Was there a seal, an impermeable cap rock, typically shale or salt, that trapped the oil and prevented it from escaping to the surface? And critically, did all of these elements exist at the same time and in the right spatial relationship? A source rock that matured after the trap formed is useless. A reservoir with no seal is a leak. A migration pathway that bypasses the reservoir delivers the oil somewhere you cannot reach. This is the petroleum system event chart, one of the most powerful tools in exploration geology. It plots the timing of every critical event: deposition, burial, maturation, migration, trap formation, on a single timeline. If the trap formed after the oil migrated through, the basin fails. If the seal was breached by faulting after the oil accumulated, the basin fails. Every element must align not just in space, but in time. Basin screening eliminates roughly 90% of the Earth's surface from consideration. It tells you where oil could exist, but it does not tell you where it actually does. For that, you need to look underground, without digging. This is seismic acquisition, and it is the single most important tool in petroleum exploration. The principle is elegantly simple. You generate a sound wave at the surface. That wave travels downward through the earth. Every time it hits a boundary between two different rock layers, sandstone against shale, limestone against salt, part of the wave reflects back upward, the rest continues deeper. By measuring exactly how long each reflection takes to return and how strong it is, you can reconstruct a picture of the subsurface, layer by layer, kilometer by kilometer, without ever seeing the rocks themselves. The earliest seismic surveys, dating back to the 1920s, used dynamite. Explosives were detonated in shallow boreholes, and the shock waves were recorded by a handful of geophones. The result was a single two-dimensional line, a cross-section of the subsurface along one narrow path. It could tell you the structure directly beneath the survey line, but nothing about what lay a few hundred meters to either side. This was revolutionary for its time, but it was also crude. Imagine trying to understand the layout of a city by walking a single straight line through it and recording what you hear. You would know the buildings directly on your path. You would miss everything else. Modern exploration uses 3D seismic, and the difference is impossible to overstate. Instead of a single line of receivers, a 3D survey deploys a dense grid of cables and geophones covering tens or even hundreds of square kilometers. On land, vibroseis trucks generate the signal, controlled vibrations sweeping through a range of frequencies synchronized with the receiver array. Offshore, a seismic vessel tows multiple streamers, cables up to 12 kilometers long, each studded with thousands of hydrophones. Compressed air guns fire behind the vessel, generating acoustic pulses that penetrate the seabed. The raw data from a modern 3D survey is staggering, terabytes of information recording millions of individual seismic traces. Processing that data into a usable image takes weeks or months of computation on supercomputing clusters. But the result is a three-dimensional model of the subsurface, a cube of data that geoscientists can slice, rotate, and interrogate from any angle. But seismic alone is not enough. Sound waves tell you about rock layers and structures, but they do not directly tell you what is inside the rock. Is the reservoir sandstone or limestone? Is it porous and permeable? Or is it tight, with no space for oil to accumulate? Is it saturated with hydrocarbons, or is it full of water? To answer those questions, the exploration team layers in additional data. Gravity surveys measure minute variations in the Earth's gravitational field. Dense rocks, like igneous basement, exert a stronger gravitational pull. Thick, less dense sedimentary basins produce a weaker signal. A gravity survey can reveal the shape and depth of a sedimentary basin across hundreds of kilometers, showing you where the thickest sediments and therefore the greatest potential for source rocks are located. Magnetic surveys measure variations in the Earth's magnetic field caused by different rock types. Sedimentary rocks are generally non-magnetic. Igneous and metamorphic basement rocks are strongly magnetic. A magnetic survey can map the depth to basement, telling you how thick the overlying sedimentary pile is and identifying fault structures that may form migration pathways or traps. This integration, seismic, gravity, magnetics, surface geology, geochemistry, and any existing well data, is called play-fairway analysis. It is borrowed from the oil industry and now used in geothermal exploration as well. The principle: systematically map the risk across a basin by evaluating every element of the petroleum system in every location. Where all the elements align, the source rock is mature, the migration pathway exists, the reservoir is present, the seal is intact, you have a prospect. And it is at this point, after years of geological study, after terabytes of seismic data, after countless hours of interpretation, that the exploration team makes its recommendation: drill here. But before a single drill bit touches the ground, there is an entirely different kind of exploration that must take place: legal exploration. Oil and gas rights are not automatic. In almost every country on Earth, the hydrocarbons beneath the ground belong to the state, not to the landowner above them. To explore for oil, a company must first acquire the legal right to do so. Governments award exploration rights through licensing rounds, competitive processes where companies bid for the right to explore specific blocks. The bids typically include a work commitment, a promise to shoot seismic, drill wells, and invest a minimum amount of capital within a defined time frame. The winning bidder is awarded a production sharing contract or a concession, the legal framework that governs their exploration and any subsequent production. But exploration is expensive. A single deepwater block can require hundreds of millions of dollars in seismic acquisition and drilling before a single barrel is produced. So companies frequently share the risk through farm-in agreements. One company, the farmer, has the license but needs capital or technical expertise. Another company, the farmee, acquires a partial stake by committing to fund a share of the exploration costs. The result, risk is spread across multiple balance sheets, and prospects that would be too expensive for any single company to drill become viable. Basin screening and data acquisition, $2 to $5 million. 2D seismic survey, $5 to $15 million. Land, $10 to $30 million offshore. 3D seismic survey, $15 to $50 million. Land, $30 to $150 million offshore. Exploration well onshore, $10 to $30 million. Exploration well shallow water, $30 to $60 million. Exploration well deep water, $60 to $150 million. Here is the scale of the bet. By the time a company is ready to drill an exploration well, it has already spent years and tens of millions of dollars on seismic acquisition, geological studies, basin modeling, and license acquisition. The well itself is the single largest expense in the exploration cycle, and if it comes up dry, every dollar spent to that point is gone. This is why the geological work matters. This is why the seismic interpretation matters. This is why basin modeling and play fairway analysis and gravity surveys and magnetic mapping all matter. They are not academic exercises, they are risk reduction tools, each one designed to shrink the uncertainty before the $100 million moment of truth. A well-targeted prospect, one supported by high-quality 3D seismic, integrated with gravity and magnetics, modeled rigorously, and located in a proven petroleum system, might have a 30 to 50% chance of success. A frontier wildcat drilled on sparse 2D data in a basin where no oil has ever been found might have a 5% chance or less. The difference between those two numbers is the value of exploration geoscience, and it is measured in billions of dollars. The geoscientists have done their work. The seismic has been interpreted, the basin model has been built, the prospect has been mapped, analyzed, modeled, reviewed, challenged, and endorsed. The license has been acquired. The partners have committed their capital. The rig has been contracted. The drill bit is turning. Everything we have covered in this episode, the basin screening, the seismic surveys, the gravity and magnetic data, the play fairway analysis, the license rounds, the farm-in agreements, has led to this single moment, the drill bit touching the earth, and now a new set of questions begins. How deep is the reservoir? What is the rock quality? Is there actually oil in the pore spaces? How much? Is it producible? And the only way to answer those questions is to drill through kilometers of rock and bring samples back to the surface. That is the subject of episode 3. We go to the rig, to the noise, the mud, the pressure, and the precision engineering that turns a geological prospect into a physical hole in the ground. The drill bit, the casing strings, the blowout preventer, and the people who run it all at enormous risk under enormous pressure because the well does not care how much money is at stake. This is CRUDE, a SeaMayors documentary series. Episode 3, The Rig, next week. If this deepened your understanding of how the industry works, subscribe and earn on notifications. And I have a genuine question for the comments. If you have worked in exploration, on seismic crews, in interpretation at the rig site, what is the one thing that surprised you most when you started? What do the textbooks never capture? Drop it below. Let us build a resource from real experience.